Welcome back, everybody. Today we're going to talk about mole ratios and mole conversions to answer the essential question, how can we use the mole concept to convert between units? Okay, so to recap what we started talking about last time, we talked about the mole, which is a unit of measurement in chemistry, the most important, which represents 602 sextillion, 200 quintillion particles. In scientific notation, that's much nicer to write, 6.022 times 10 to the 23rd, also called Avogadro's number. We also talked about the molar mass, which is the mass of one single mole of a substance. The molar mass of each substance is different. So the molar mass of hydrogen is 1 gram per mole, but the molar mass of helium is about 4 grams per mole, and the molar mass of palladium is 106.42 grams per mole. So it's a little different depending on what you're talking about, but we can always find the molar mass by adding up the atomic weights of each atom in the substance. So for example, Br2, bromine, is made out of 2 bromine atoms. So this molecule bromine is made out of 2 atoms of bromine. So we can take the molar mass of one bromine plus the molar mass of a second bromine to find that the molar mass of Br2 is 159.808 grams per mole. So if you have 1 mole of that substance, this is how many grams it is. Okay? So to represent that, you can think of the mole as sort of like a measuring cup for particles, which helps us keep track of mass and particles and molecules. So this 1 mole bromine is 159.808 grams. We know the atomic weights because we can find them on the periodic table, right? And that helps us find the molar mass. Okay, so as I was explaining before, the mole is the most important unit of measurement in chemistry. Super important, because using the mole we can convert between many different units very conveniently. We will only talk about a couple of conversions today, but there are many, many more. All right, so the mole is the center of all units in basic general chemistry. Okay, it can be abbreviated MOL, just a little note here. Now we can convert between moles and particles by multiplying by Avogadro's number, because each mole has this many particles in it. So the particles per mole is 6.022 times 10 to the 23rd. Now if we can multiply to go from moles to particles, that means we can divide to go from particles to moles. So division is the opposite of multiplication. So if you know the number of particles, you can divide by Avogadro's number to get back to moles. Okay. Now, if you know the molar mass, we can go between moles and grams. Okay? If you multiply by the molar mass, which is units of grams per mole, all right, which you can find by summing or adding up the atomic weights of the compound, you can get to grams. Okay? If we can multiply by the molar mass to get to grams, that means we can divide by the molar mass to get back to moles. All right? Again, the molar mass being units of grams per mole, how many grams you have per mole of that substance, which you can find by adding up the atomic weights from the periodic table. The mole is the center of it all, so the mole is really important to chemistry here. All right, so all of the problems we're going to solve in this unit are called stoichiometry problems. It's converting between amounts of different molecules using chemical equations. For every single one of these problems, these 3 steps will really help you out. First step, which is a general good step for all problems, is identify where are you starting from? What are your starting units? Are you in grams, moles, particles? What are your units? And what are your desired end units? Are you in grams, moles, or particles? Okay. Second step here, if you don't know moles, if you're not given moles or you haven't found them yet, always convert to moles as your first step, because the moles is the center of this whole thing. You can go from moles to particles, you can go from moles to grams, you can go from moles to molarity, you can go from moles to volume, all sorts of things, very useful. And then for this last step here, if you're not sure where to go next, decide where you're going to go next and how you're going to get there based on what your current units are. So if you're in grams and you want to get to particles, all right, you know first you're going to have to go to moles because that's our second step, always convert to moles. So we're going to have to divide by the molar mass of whatever our substance is. And then to go from moles to particles, we have to multiply by Avogadro's number. Okay. This is a very useful graphic in helping us learn, but it will not be on the test, so get used to doing these problems without it if you can. Okay, so let's talk of an example. So let's say you have 32 grams of helium, right, element number 2 on the periodic table. How many moles is this? Okay, so let's identify what are the starting units. We have grams, okay? Grams is what we're starting with, so this is our starting point, okay? That's our start. Now, let's identify our end units. It says how many moles is this? So moles is our end unit. So this is where we want to end up at. Now, we have identified where we're starting and we've identified where we need to end. Okay, this is the first step, the most important step. So now we can identify how we get between grams and moles. We can follow this nice glowing arrow that shows us the direction from grams to moles. Okay, follow the direction of the arrow to the place you want to go. Right? So we now know that we need to divide by the molar mass. So we need to find the molar mass of helium. So if you're looking off of your periodic table, which you should have with you in the back of your packet, right? The molar mass of any substance is the sum, meaning the addition of the atomic weights. Helium is only made of one type of atom. It's just an element. And its molar mass, meaning its atomic weight, is 4.003 grams per mole, which we can find on the periodic table. All right? So that's the molar mass of helium. So now I'm going to show you something called conversion bridges. All right? This is a method of showing the cancellation of units in each step of a problem with unit conversions. Now, in these early problems, you may see, like, I don't need conversion bridges to do this. This is really simple math, Mr. Kurt. But I'm going to tell you right now, conversion bridges is probably one of the most useful mathematical tools in chemistry. Right? Very useful. It helps us organize our thinking. Right now, these problems are simple enough that you don't really have to organize your thinking to know what you're doing. All right, so these early problems will be very easy without organizing our thinking, but later on, this conversion bridge method will really help us. All right, so don't forget your bridges. They take us from one place to another. Okay, so now that we know where we're starting from, we have grams, and where we end at, we know we got to get to moles. Let's start filling in our information. So 32 grams is what we start with, and in the previous step, we decided that we're going to have to divide by the molar mass of helium, which can be found on the periodic table. This is its atomic weight, which is also its molar mass. So helium is 4.003 grams per mole. Now, the way we have this problem set up, 32 divided by 4.003 will give us our correct answer. But I'm going to be working on teaching you conversion bridges. All right. So first thing I'm going to do is I'm going to move the units around a little bit. All right. Try to keep track. Saying per mole is the exact same thing as writing it as a fraction. Okay. So you can say per mole. This is what it also means. Exact same thing. 4.003 grams per mole. Now, if you are familiar with your math facts, dividing by a fraction is the exact same thing as multiplying by its reciprocal. The reciprocal is if you flip the fraction. Switch what's in the top and what's in the bottom. Switch what's in the numerator and the denominator. Then you can flip your sign. So from division, we've gone to multiplication. The reason we're going to do this is because now this makes things very convenient to see that grams cancels out. So conversion bridges help us tell what units cancel and what units are left. So before we solve this problem, which is admittedly pretty easy, right, we know that our final units are going to be moles because that's the only unit that has not been canceled out. That's what's left over. So we can check our work and know that we did the right work because we can cancel the units that don't belong and keep the units that do. Now when you finish this problem, it's written as 7.99 moles. Okay. So these conversion bridges are set up so each number in the top row is multiplied. That's why we flipped the fraction. We did the reciprocal. So everything in the top is multiplied, and everything in the bottom we divide by. Okay? So 32 grams times moles. So we have moles as part of our units now. Divided by 4.003 grams, gets rid of grams as our unit. And now we're left with 7.99 moles. Okay? It's a little confusing to look at it first, but just try and get used to it little bit by bit. So let's try another problem using conversion bridges. In this case, we're asked how many particles are in 3.5 moles of iron. So first step, identify what are we starting with? Moles, 3.5 of them. Where are we ending? Particles. We don't know how many particles just yet. Okay. Now, let's set up our bridge. Now remember, these are written so that every number in the top is multiplied across, and then we divide by each number in the bottom. Okay? That's the goal here. Okay? So, in order to get across, we have to multiply by Avogadro's number. So we'll multiply by 6.022 times 10 to the 23rd particles per mole. So we put that in the top because we're multiplying. Now remember, we can also take that per mole and switch it to the bottom. All right, that's the exact same thing. And now, using our conversion bridges, we can see that moles cancels with moles, and we are just left with particles. So this is how we can check to know that we set it up correctly. It's the only unit that does not cancel is our final desired unit, particles. Okay, so we know that's 2.1077 times 10 to the 23rd particles. Okay, This one involves a couple of steps here. We're asked how many particles of gold are in 287.5 grams. Okay, so our starting point here is grams. This is our start. And our ending point here is going to be particles. So we're actually going to have to do 2 steps here. Okay, let's start by setting up our bridge. So 287.5 grams of gold here. Remember, these lines written here are to separate what we multiply by, each thing in the top, and we divide by each thing in the bottom. And we want particles as our final answer. Okay, first step here is we're going to need to divide by the molar mass, which again is the sum of the atomic weights. Now, since gold is just an element on the periodic table, its symbol is Au for aurum, we can divide by the molar mass. So we know we're going to divide by the molar mass, 196.967 grams per mole. Okay, now remember, we can move that mole to the other side. So saying per mole, we can switch where it is. Okay, so now we can write our second step, which is to multiply by Avogadro's number. Since we're multiplying, we put it in the top. All right, it goes in the top, particles per mole. Now that mole again, we can switch to the other side. Okay, so now we set it up so that we multiply by each thing in the top and we divide by each thing in the bottom. Okay, now we can check our conversion bridge to see if we set up the problem correctly. Grams cancels with grams, moles cancels with moles. Anything divided by itself is just 1. So grams divided by grams, grams goes away. Moles divided by moles, it just goes away. So now we're left with particles as our final answer, which we know is exactly what we are looking for. Okay, so then when we do the math, we'll take 287.5 divided by 196.967 multiplied by what's in the top, 6.022 times 10 to the 23rd. And this will end up with 8.79 times 10 to the 23rd particles of gold. All right, so those mole conversions we'll talk more about, and those conversion bridges we should work on trying to understand. It's a really useful tool for helping us learn stoichiometry. Now when we talk about the mole ratio is a ratio, okay, a relationship between numbers, showing the relationship between the amounts of molecules or particles in a balanced chemical equation. Okay, so for example, let's talk about cooking, because balanced chemical equations are like recipes. In cooking, if a recipe says you need 2 cups of flour and 1 cup of sugar to bake cookies, the ratio, meaning the amount of flour to the amount of sugar, is 2 to 1, because you need 2 cups of flour for 1 cup of sugar. So every 2 parts of flour that you add to this, you need 1 part of sugar. As a visual representation, here's our flour and here's our sugar. And in the end, we will make cookies. All right, delicious cookies. Hopefully you don't forget those chocolate chips. Okay, so now going from the recipe to the balanced chemical equation, we're going to talk about how do mole ratios help explain how much of each ingredient, reactant, in this case H2 molecules and O2 molecules, is needed to make a certain amount of product, in this case water. So if we want to know the ratio, the mole ratio, of H2 to O2, it's just going to be 2 to 1, all right? So what this means is for every 2 moles of H2 that we have, if we want to complete this reaction, we require 1 mole of O2. Just like with those cookies, if you got 2 cups of flour, you need a cup of sugar to make those cookies. Otherwise, they're just going to be flour, all right? Now, if we want to know the ratio of H2 to H2O, all right, same thing. Just take the coefficients, all right? So for every 2 moles of H2 we produce 2 moles of H2O, assuming we have enough of our other ingredient, which is O2. Okay. Same thing with cookies. If you got 2 cups of flour, you might expect to make 3 cookies, but that's only if you've got enough sugar. Okay. Now for this last part, O2 to H2O, again, we'll just take the coefficients. It's 1 to 2. So for every 1 mole of O2, we produce 2 moles of H2O. Again, assuming we have enough of all of our reactants. So if we have enough H2 to make that happen. All right. All right. As another example here, let's talk about the burning of propane. So if you like to grill out on a propane grill, this is the reaction that causes your grill to get hot. Okay, so let's first look at the ratio of propane to oxygen molecules. In this case, for every 1 mole of propane that we burn, we need 5 moles of O2 to react with it. So you need oxygen to have any fire. Okay. The ratio of propane to carbon dioxide is 1 to 3, so for every 1 mole of propane that you burn, you produce 3 moles of CO2. Again, this is assuming you have enough of this ingredient to actually do anything. Okay. The ratio of propane to water is 1 to 4, so every 1 mole of propane that burns, we produce 4 moles of water. This is again assuming we have enough of our ingredients, our reactants. The ratio of O2 to CO2 is 5:3, so for every 5 moles of O2 you burn, there's 3 moles of CO2, again, assuming you have enough of the other reactant. The ratio of O2 to H2O is 5:4, so for every 5 moles of O2 that you burn, you produce 4 moles of water. And lastly, the ratio of CO2 to H2O is 3:4. So if you know you produced 3 moles of CO2, that means there's also got to be 4 moles of H2O produced. All right? Okay. That's it. When you're ready, take the checkpoint quiz. Otherwise, I hope you have a wonderful one. Take care, chemists.